It's a pleasure for us to participate in this webinar with Gurobi today. I'm going to start off with talking a little bit about Princeton Consultants. So we are a Gurobi Premier Service Partner. I think we were one of the first partners to achieve that designation from Gurobi, and we're quite proud of that. Our firm has been in business for over 43 years. We have our roots in management consulting, but we've, over the time, started using information technology to help people make better decisions and integrate these decisions with technology into their business. We now talk about AI. We think a lot of times AI and optimization is part of AI. We've done many successful projects in a lot of different industries. We have some long-term strategic relationships with top transportation clients, especially in the railroad industry. And we have a lot of people who've been around here a long time. Coming in December, have been at Princeton for 10 years. There's a lot of people who've been here a lot longer. So we retain our staff pretty well in terms of delivering this value to our customers. A little bit background about me. I was one of the original developers of CPlex way back in the 90s, and I moved in my career through product management and marketing. And then at the time that iLog was purchased by IBM, I was in charge of all the sales and outbound marketing for iLog's optimization and visualization products, which included CPlex. So I was on the business side. And then after the IBM acquisition, I was working to integrate the iLog business into IBM. And then I spent my last few years in IBM research, getting back my technical chops and looking at what would be the next frontier of things. Been honored to be a certified analytics professional as designated by Informs. I'm an Informs fellow and now a senior member. And what's relevant to today's talk is I'm also a member of the Pandas core team. Discovered Pandas about 8-9 years ago and realized that it was going to solve a lot of problems for me in terms of how we would develop optimization applications, made a number of contributions to Pandas, and then they invited me to be part of the core team. And so I understand Pandas pretty well. And the gurobi-py Pandas library that we'll talk about today was actually inspired by some of the work that we had done back around 2018 or so in tying Pandas and Gurobi together. And then Gurobi has decided to build a library for it. One of the things we want to talk about here when we talk about data-first optimization, I've taken here something that came out of a job task analysis that was done by Informs when they created the Certified Analytics Professional process, an exam about 12 years ago, where I'm actually on a committee right now that's revising these tasks, but the fundamental 7 domains that you see here remain the same. And we like to talk about that if you're developing a solution for analytics or optimization, that you start off with finding the right business problem or question that you want to solve and framing it as a business problem. Then you turn that problem into an appropriate analytics problem. Then you start working with data, pick an appropriate methodology, optimization, hopefully, but it may not be optimization. Then you get into building your model, and then you get into deployment. And deployment is building out a technical system that would stand up an application, or also deploying some decision support system and figuring out how the business has to change things. And then lifecycle management is how does it live on over time, and how does it have to get modified? The reason I wanted to include this in today is that I wanted to point out that this process is about doing data before the model. And unfortunately, this is not the way we typically teach optimization in the OR community. We always talk about models, but in a good process, and this is a proven process, not only from this job task analysis, but it's something that we'll dive into a little bit more deeper as a successful methodology we use here at Princeton Consultants, is that we start with the data and then we start worrying about our modeling. So I'm going to illustrate that with an example. And then about halfway through, I'm going to turn it over to Simon for another example that illustrates some more of the features with gurobi-py Pandas. So our data-first model development approach is listed here, and this is a 7-step approach that we have found improves the likelihood of success in our optimization projects. This approach ends up creating some very useful documentation, not only for our team so that our team can, different members can understand what's going on, but also so that our clients can understand. We found that it shortens our overall development time, makes the code maintainable over time, and also provides a natural feedback loop over to business requirements. And I'm going to illustrate these by the example. We first go off, once we're in the data part, about understanding the data. We define and document the data sets, then collect some data from a client. We document data transformations. Often the data that you get needs to be transformed in different ways in order for it to work for optimization. Then we create documentation of the model. This is writing out the math of the model. And then we write the code of the model using gurobi-py pandas. And finally, we look at results and we make sure that the results make sense and iterate. Potentially, we may have to change some of the data. We may have to see if our model is correct, etc. But I'm going to be concentrating today on steps 1 through 6, which are about working with the data and coding an optimization model, which is using a data-first model development approach. So I'm going to start with a very simple example, and this example is inspired by an example that comes with Gurobi called netflow.py. So in this example, it's a very simple multi-commodity network flow problem where there are 2 products, pencils and pens, that are produced in 2 cities, and they must be sent to 3 different warehouses in 3 different cities. The nature of the network is that every production point, Detroit and Denver, can ship to the 3 different demand points. There's no intermediate points. You have to satisfy all supply and demand. And then there are capacity constraints. So on each connection, there are a limit on how many total pencils and pens you can ship. And the overall goal is to minimize the sum of the ARP transportation costs. So this is a model that we often see in a beginning linear programming course, and is an example, as I say, that comes with Gurobi. Now, as I get into the example, I want to mention that we are assuming that you are familiar with pandas. So I'm going to be using pandas things, and if you're not familiar with pandas, then it's time to learn it because it really is the best way to be working with data. But let's first take a look at this example that comes with Gurobi and see why it's not that great, in my opinion. And I would argue that this is a poor data representation. So the first issue is that the data is inside the code. When you write real applications, you want to set data. Typically has a data source, whether it's an Excel file, CSV files, database, user inputs, JSON. It could be any number of different things, but it does not live inside your Python code. The second aspect is that this data structure is very much dependent upon the Gurobi multi-dit structure, which is useful if you want to go very much directly to the Gurobi API. But again, it is now linking you to Gurobi in terms of your data representation. And we want to use data tools like Pandas for data and use Gurobi for what it does best, which is optimization. The next aspect is that the sets of commodities and nodes are really repeated. If we look at all the data for the ARCs and the cost and the inflow, we can infer the list of commodities and the list of nodes. So in a data-first approach, we don't repeat data that can be inferred from other items. So that's another issue that appears here. Another aspect is mixing supply and demand data. So you'll see I've copied the comment over from the example where the supplies are positive and demand is negative. But in reality, if you're working with a client, they're going to have a separate table that says, here's how much we have available at various our production facilities. Here's where our demand points are. Those are all going to be positive numbers. This is set up this way to make the model easier to state in the Gurobi example so that you really effectively have assumed that somebody's transformed supply and demand in here. Secondly, the other issue with this representation is that if you had a large network which with a lot of intermediate points, which happens a lot in the trucking industry, where there are different places that freight can be interchanged, what you would end up having to do in this representation is have a 0 value for every single combination of nodes and products and nodes that would make this inflow array or dictionary very, very large. So now let's talk about how you would handle this in a data-first approach. So first, I've chosen an approach that let's store all of this data in Excel. So I created an Excel file that has 4 tables. Here's the capacity table, and I've labeled the nodes as from and to, so that we know where it's. We have capacity on the arcs. We have the cost of each arc for each product. We have the supply for a variety of nodes, and we have the demand for each of the nodes corresponding to each product. So this is a tabular data representation. I've chosen Excel, but it could have been in CSV files. It could have been in a database, whatever would be your convenient table representation. At the bottom, we can see the Pandas code that reads this in. So one of the things that really got me excited about Pandas was being able to say, here are 4 tables, and in one line of code, pd.read Excel, I can read all of that data in. And the result of this, because I said sheet name equals none, means I get a Python dictionary indexed by the names of each of the tabs that is going to contain the that's going to contain a data frame corresponding to each one of the tabs. So the code below here is now transforming those data frames into series. If we look at this particular set of data, we can see that the numeric values are all in the last column, and the indices are in the first set of columns. So this 4 lines of code that you see here is basically going to transform those data frames, saying set the index of them to be all the columns except the last column, pick out the last column, and that will become a series. And now we have a dictionary of Pandas series indexed on our capacity, cost, supply, and demand, the names of our tables. And and the values in the dictionaries are going to be series with the things that are in bold as indices. So here's what this would look like in Pandas. I've actually printed it as data frames to see that what we have here are the indices, like in capacity, are from and to, and the capacity values. Similarly for cost, the indices are product from and to with cost and supply and demand. One thing to note here is we take really good advantage of the Pandas multi-index capability, which is essentially a sparse representation of various tuples. In this particular problem, all possible values are there, but the particular model that I've actually built will work if you did not have all possible combinations of products and products going from every node to every other node, or you didn't have supply at every node, or you didn't have demand at every node. Our next step, and I've mixed 2 steps here together, we typically have a separate document that will document the actual model of the data. And here I've combined that with our mathematical notation that we're going to be using as we develop our model. So what we see here is that I'm going to have a set of nodes. The nodes appear in 4 different tables: the cost, the capacity, the supply, the demand, with the associated columns that correspond to nodes. We have the set of products or commodities, which come from the column product in the 3 tables: cost, supply, and demand. We have a set of arcs. The arcs are going to have a from node and a to node, and they will come from the cost table with from and to. And then we'll have we're going to compute 2 sets, which are inferred. Basically, for every arc, we want to know which products can go on the arc. And we can know that from the cost table. And similarly, we want to know for every product the set of arcs that are eligible to ship that particular product. We're also going to notate with some math notation the numerical values that we will need. So as I mentioned earlier, the data is all converted to Pandas series. So the name of each series is also the name of the value. So here, the capacities of the arc I've called kappa, will be indexed on from and to, and that'll be called capacity. We have the cost of carrying product P, I've called pi, for every arc and every product associated with that arc. We have sigma, which is going to be the supply of the product P at node N, and the demand, which is delta, which is for product P and node N. And if a specific product and node combination isn't supplied, we assume that the supply and demand are equal to 0. One of the conventions that we use at Princeton is we use calligraphic letters to represent sets, and we use lowercase Greek letters to represent numerical values. So in the data first approach, what we do is we infer the sets from the data. So as I mentioned earlier, the set of products can appear in any of the tables, supply, demand, and cost, and the set of nodes can appear in any of the tables, capacity, supply, demand, and cost. So what you see here is some Pandas code, nothing to do with Gurobi, that's computing those sets. The first computation for the set of commodities is basically taking advantage of the concat operator. This is going to take each one of the series that has product in it, which are supply, demand, and cost, concatenate them together one after the other, and then compute the set of unique products. Similarly, for the nodes, we're going to rename the, for each from and to, we will rename it to node for each of the capacity and costs. And then what we will do is we concatenate those nodes with the nodes that will appear in our supply and demand. So this is, again, Python and Pandas computing the data, the index values, our set of commodities and our set of nodes directly from the tables and not specifying it separately, which is what you often see with modeling languages like AMPL or OPAL or GAMS. The next thing that we have to do here is, how do you compute the net flow? So we mentioned that this net flow is what we want to think about. Is the net flow is going to be how much you take out, ship out of a node, less what you take in for a node for each product and node. And for the nodes that are in the middle, that value will be 0. So we're going to call that inflow. We're going to use the same naming convention as was used in your original Gurobi example. And what we're doing here, again, is using the Pandas operators, where what we first do is we take the supply values, we're going to call that net. We take the demand values and we multiply them by -1 and call that net. And then we're going to add another series that has value 0, which combines all the possible products and nodes. We take this long series of supply, demand, and values of 0, and we use the Pandas group-by operator to basically say, give us the sum of these values for every product and every node. So again, this is a standard Pandas operation that you use to concatenate data and compute the total sums. One of the things that's nice about this particular representation, and it's illustrated, we have this example will now be on the Gurobi Pandas website, is what will happen is, if in the second data set, I made it where some of the products don't exist at some of the supply points or don't exist at demand points, or sometimes there's a point that has both can produce one product and have demand for another product. So this representation is allowing supply and demand to coexist at the nodes, and for any of the nodes to act as transshipment nodes. So I'm thinking about, what could the data look like in such a way that I can make my model generic enough and not have it depend on the specific data instance that was given to me. And this is something actually that's not true, this ability of having transshipment nodes in the original Gurobi example. So now we're up to step 5, which is to create the mathematical model for our problem. So it's a very straightforward model, and we write out the mathematical notation for it. We'll have a set of decision variables X indexed on the products and for each arc for that product, which will represent the amount shift of product P on arc A. And we'll call that variable flow in the code. The cost of a shipment, as we know, is pi AP, which defines our objective function, which is to sum over the arcs and then sum over the products that are on those arcs, the cost times the amount shipped. And then we're just going to have 2 simple constraints. The first constraint says for every arc, we're going to sum over the associated products and say the sum of the flows is less or equal to the capacity. And then the final constraint is basically the conservation of flow. So what we want to say is that the flow out of the node, for a node N, the flow that goes into any 2 node for a specific product, less the flow that comes out of a node for that product, is equal to our net flow. And we state this for every product and for every node. And this will also include transshipment nodes where we might have a net of 0. So now let's take a look at how this is implemented using gurobi-py pandas. So up at the top, you'll see the 2 imports that are needed. For a long time, I was always using GRB, and I still do when I import gurobi-py. I think Gurobi likes using GP now. We like gurobi because it reminds me of Gu, Rothberg, and Bixby. And the new library that is now supplied is gurobi-py pandas, which we use GPPD. We've already imported pandas. We now create the model just like we always did. And now we're going to create the set of decision variables. And the way this works is we say, okay, gurobi-py pandas, you're going to add variables to this model M, and data of cost is going to tell you the index of the variables. And then the objective function in this particular case, since we already know it, you can say the objective coefficients come from data of cost as well, because data of cost is a series that has the indexes of our products, our from and our to nodes, and it has the cost values. And what this will do is create a series that you see here. And this is a Pandas series that, instead of containing numbers, contains the decision variables of our problem. And by doing this, we'll be able to take advantage of a number of Pandas operators to make it efficient in terms of being able to state the model. Now let's take a look at the first set of constraints. And I'm going to walk through each part of this so you understand how to map the math of a simple constraint that you see at the top over to both Pandas and gurobi-py pandas. So first, flow, you'll see here, is specified as our x variables. The next thing that we're going to do is we know that we have to state this for every arc. We know that the flow has an index of from and to, so the group by operation you can think of as take all the flows and group them by from and to, and then sum them up using the gurobi quick sum operator that is going to add up and give us a series that will correspond to the expressions that add up the flows for each pair of from and tos. So if you remember, our flow variables have product, from, and to. So we sum over the products, which is what we've done here by grouping by the from and the tos. We concatenate that with the data of capacity, which is our capacity values. So here was the sum, and now we have the capacity values that are on the right-hand side. The axis equals 1 says line them up all next to each other. Then we can simply state the constraint. So what gurobi-py pandas does is added accessors. It says this is a data frame. Use the gurobi-py pandas to add constraints to our model, and we can simply say that flow is less than or equal to capacity. It's not the same flow, because when we do the flow, group by, and ag operation, we still end up with a series that's named flow, but gurobi-py pandas interprets this and knows that it has to state the constraint and that its name should be cap. You can see this in the data frame on the bottom. It's indexed by the from and to nodes. The flow is the sum. We can't see the entire sum here, but the first sum is the flow of pencils from Denver to Boston plus the flow of pens from Denver to Boston. The capacity is 120 from our data, and then we've created a constraint which is actually now inside of this data frame, and it has the complete expression of flow, the sums, less than or equal to capacity. Now let's take a look at the conservation of flow constraints. I've written it again up here on the top, and I've also repeated the mathematical expressions here on the right so you can see how they work. So let's take a look. So first of all, we're going to be stating this constraint for every product and node. So when we do group by operations, we're going to see product and node. We take the flow and we're going to rename the axis. Instead of calling it, we're going to call what's in the from column. We have product from to. We're going to call that node, because we want to get we're stating this for each node. So we rename from to node, we group by the products and nodes and take the sum, and we're going to call that flow out, which will correspond to the first sum. Similarly, for the inbound flow, we're going to rename the index from to node, group by the product in the node and sum up the flows and rename that to flow in, and that's going to give us our second sum. We're concatenating these together with the inflow, which is our net flow. And then we say axis equals 1. I'll explain the fill in A0 on the next slide. We use GPPD again, gurobi-py pandas, to add the constraints that says the flow out, the first sum, less flow in, the second sum, is equal to the net, which was our inflow, which is what we called inflow when we computed it, and now we'll call that the node constraint. What we get as a result of this is the data frame you see above. You'll see it's indexed on product and node. We have the flow out, which is all the flow coming out, and the flow in, which is the flow coming in, and we have a constraint. Now, in this case, there were no transshipment nodes. In fact, when I first ran this, I said, wow, look, all the flows go from the producers to the consumers. But what we need here is, if I do this, when we do this concat operation, there were no flow in values for pencils and Denver and pencils in Detroit, because those are supply places. So we would end up with NA values where you see the zeros. By putting the fill NA 0, we're basically saying if something is missing because we're joining what the out and the in is, change that value to 0. And then we can write the constraint that says flow out minus flow in equals the net. And what you will sometimes see when you're using gurobi-py pandas, if you forget to do the fill NAs, then when the model gets past the gurobi will say, or gurobi-py pandas will say, hey, you've got an NA value in here. I don't know what to do with it. And therefore you have to fix it typically with a fill NA operation. Finally, we want to optimize. And when we optimize, we do the normal optimization. And then you can see that the accessors, we have flow, we can say .gppd, this is our gurobi-py pandas, and we can get the attributes of any particular series, in this case, X. If I wanted to get reduced costs, I could have said .rc, and whatever attributes exist within gurobi can be then applied to that series. And now I can say, let's use pandas to query and say, give me all the flow values that are greater than 0. Let's sort the indices so we have products before the pens. And then we end up with this nice table that gives us our answer to our optimization problem. So I've now gone through kind of the simple example of how you use gurobi-py pandas. I'm now going to turn it over to Simon from Gurobi, who's going to go over a more complex example. And Simon, the floor is yours, as is control of my laptop.
Thanks very much, Irv. So briefly by way of introduction, my name's Simon. I work on the development team at Gurobi, and one of my main jobs is working on our various Python APIs, which is great fun because we have really nice libraries like Pandas to integrate with, and we can pull off all these nice tricks that I've just shown you. I'm also based in Australia, so I'm speaking to you from Melbourne. You'll notice me use the word data a lot rather than data. Sorry about that. I hope it's reasonably understandable. So I wanted to spend the next 15 minutes going through another brief example of using gurobi-py pandas just to show off a few more modeling techniques that you can pull off with this library. The example I'm going to walk through is called the unit commitment problem. This is a classical operations research problem. You'll find it in a lot of textbooks. This particular example is actually from a textbook, and you can find it on the gurobi-py pandas documentation page. The goal of this problem is that we have an electricity network that has an expected demand that needs to be met by a number of generators. And we need to decide, the optimization problem needs to decide how to dispatch those generators to meet the target demand. There's additional constraints around keeping, say, an amount of reserve capacity online for a given set of generators in case the expected demand significantly exceeded. And we want to minimize the overall cost of the whole system, the cost of turning on and off generators, the cost of the actual power generation, and keep within some sort of physical limits of the generators themselves. This is quite a simple form of this problem that arises in power systems operation. There's a lot more complex constraints in real life, but I'm just going to walk through kind of the key parts of this model. And let's make sure I can move the slides along. There we go. All right, so my goal here is to just illustrate the model building techniques mostly, so I'm going to skip over a couple of the steps that I've illustrated in detail around sort of handling the data, reading in the data. And I'll assume I've already got my data sets in Pandas and ready to go. So the key thing here, as I've said, we're modeling these problems data first. So I've got as inputs to this problem a table, a data frame at this point once I've read it in, showing the data related to all the generators. So generators in this problem come in classes. I've got three different types of generators here, each with different characteristics. They have different fixed costs, different marginal costs related to what they're generating and what it costs to start them up. And they have lower and upper generation limits when they're online. And for each one of these generator classes, there's a maximum number of them that can be online at a given time. Over on the right, I've got data for time periods. So this is a time-based model where dispatching generators over discrete time intervals. So each of my time periods has an expected demand, and it also has a minimum active capacity, so a level above the expected demand that we want to make sure enough generators are online and capable of meeting if that expected demand is exceeded. And what the model is going to do is construct a state for each generator class for each time period. So the two key indexes that I've got here in my data frames for the generators and the time periods, we're going to need to construct a cross product of them so that we can track the state of each class at each time. Right, just waiting for slides to move along. There we go. Right, so I've got a bit of explaining to do of this little bunch of code. So this is the code snippet to construct all of the variables that I'm going to need in this problem. So there's a couple of steps here. The first is to create a multi-level index that I need for the problem. And that's created using an inbuilt Pandas method called fromProduct. So as I mentioned, there are two indexes in this problem for time periods and for generators, and I need to create a state for each generator in every time period, and I do that just by forming the cross product of those two indexes. And that's done just using a Pandas operation. I join the generator data onto this index to make sure I've kind of replicated all the data. I'll show in just a moment why I've taken that approach. And then what gurobi-py Pandas provides for us here is the ability to create these accessor functions that Irv's already showed to create new variables to add to the problem. So each of these method chained accessors that I've got here will create a class of variables, so one variable per entry per row in the data frame, which will capture the state of my generators. So I've got a continuous variable tracking the output of each generator class, the total output, a discrete variable tracking the number of active generators, a number of available generators at any given time. And that's upper bounded by the total number of generators in each class. And then I've got separately a discrete variable tracking how many generators of each class start up at any given time. So the result that I get looks like this. So this is, I've essentially munged everything into one big data frame containing both variables and input data, and this is going to help me build constraints very efficiently. I've got my time expanded index. So my generator classes replicated over all the time periods. This is kept as a Pandas multi-index. All of the decision variables in the problem, they share this index. So I've got at each point in time, all of these state variables, output, active generators, and starting up generators. And these gurobi-py Pandas accessors have created all those variables for me, giving them convenient names, so this is nice and readable. And the input data from the generator classes I've expanded across this multi-index as well. So you'll notice this gives me some replication of the data. There's a small amount of overhead from doing this. I don't think it's typically significant in terms of actually solving this problem, but it will make the constraints a lot easier to formulate. Okay, so on to the first set of constraints. So the simplest physical constraint here is just to make sure that generators are operating within their defined limits. So generators have a minimum and a maximum output. So the number of generators of each class that are online is going to dictate the total output of that class that's possible. And we make these constraints pretty easy to build in gurobi-py Pandas because they're just row-wise in this time expanded data frame that I have. So generators is the data frame I was showing from the previous slide. And these add constraints calls that I have will create one constraint for every one of these time expanded rows that I have in the data frame. And this is using the same syntax that Irv's shown on previous slides for the last example. So we're just constraining that with two types of constraints, that the output of the generators sits within these defined physical limits. And the way these constraints are working on the data frame is we're really just we're defining a relationship between columns, right? So there's some input data, some decision variables, they're combined to form this set of constraints. Satisfying demand. So we have a target level of demand that needs to be met. The way this problem is defined, we meet this demand exactly in the solution. That helps us come up with our total cost formulation. And the way this is done is we need to aggregate over all the generator classes in a given time period. And we do this using one of the gurobi-py pandas add constraints helpers, which creates a relationship between two series to specify a constraint. What this particular setup is doing, so we have a left-hand side of the constraint where we see the group by. So I'm over my full time expanded data frame, grouping by time periods, collecting the output variable, and summing that up over all of the generator classes. So you can see the effect of that with these highlights at the bottom. We're collecting over the same time period different generators, summing up these results. And then we're simply setting that to be equal to the expected demand in the time period. The important thing that gurobi-py pandas requires is that the indexes of the left and right sides of the constraint that you're providing to this function actually line up. So recall that generators has this multi-index of generator classes and time periods. By grouping over the time periods and summing across the generators, the result that I get out of this group by sum operation is indexed over time periods. And my time period input data for expected demand is obviously grouped over the indexed over time periods as well. So these two things are compatible, and I can build this set of constraints. Satisfying the reserve capacity has a pretty similar style. So we're similarly grouping over time periods, summing up all of the generator outputs in that given time period. Here we're using the maximum output characteristic of a generator and the number that are currently online to capture the maximum output of all the generators which are online at a given time. I've formulated this one slightly differently. I've captured, in this case, before creating the constraint, I've captured this total active capacity metric as a separate series. So this is a pandas series that I have of linear expressions. And then I use that series directly in my final constraint to ensure that active capacity at least exceeds the minimum active capacity that I require in each time period. The reason I've done that is I'm keeping track of this for some analysis and the results later on. Okay, so on to the slightly trickier constraint. So as I've mentioned, what gurobi-py pandas does is provides a couple of accesses for adding variables and constraints, but everything we do for building models with this library is really just applying pandas operations to a data frame or a series that contains gurobi variables. And this particular case is implementing a couple of slightly more complex operations. So what we're aiming to capture here is we have these discrete startup variables that will be associated with a startup cost for a generator. And to define those startup variables, we need to track the difference between the number of generators that are active or online at a given time period and the number that were active at the previous time period. That will tell us how many were started up in a given time period. And Pandas has a couple of nice operations that we can leverage to get this constraint formulated. So the first is the group by operation. So we need to look at each generator class separately for this kind of constraint. We're looking at to figure out the number of classes of generators of class 1 that started in a given time period, and I need to compare the generators of class 1 that started in the previous time period. So my first step here is group these this data, these variables, by the class. And then on each of those classes, we'll separately apply this count startups function. And what this is doing is applying a pandas diff operation, which is just computing a row-wise diff, so a difference between one row in a data frame and the previous one. So computing the difference between the one time period and the next becomes really easy. And my startup variable is constrained to be at least as large as the difference between those two entries. So the actual entries that I'm capturing out of the data frame are these three that I've highlighted below. So num active between two time steps and num startup for the current time step. If you're wondering why this is specified as greater than or equal, so the startup variable is a non-negative integer in our formulation. So making it just at least as large as the difference will capture that it's either 0 if there were no new startups or generators were shut down, or it will capture the number of startups if there are more generators online in this time period than the previous one. And this whole operation will kind of replicate that relationship across all time periods, like a rolling window. Okay, so with that all formulated, it becomes really easy to state the objective. So I have multiple variables, each of which is associated with a cost. We have a couple of ways of specifying an objective within gurobi-py pandas. So Irv showed one of them, which is to apply the linear objective coefficients at the time where we set up the variables in the problem. The other way is to compute the objective expression as a whole. So the way this operation is done is we're summing up at each time period and for each generator the total cost associated with that combination. So I'm doing this within my time expanded data frame. I can compute the cost component from the hourly cost of active generators, marginal generation cost of any generated power beyond the minimum of each generator class. And then also the startup costs can be computed here because I've already constrained these startup variables correctly. So what we see in within the brackets here is a series creating each of my cost components by time period in generators. And then all I have to do is just aggregate that by summing these all together. See, Irv and I have used the different styles here. So I've used the built-in summation function from Pandas. Irv's applied gurobi-py's quick sum operator. There's a slight performance benefit from using quick sum. There's a note on this in the documentation. So if you're working on really large models, I think that's beneficial. But I also like kind of writing examples this way, since leveraging Pandas's operations and writing something that's kind of a clear data-oriented operation, I think illustrates this quite nicely. Okay, so final step, just briefly looking at the results we get out of this problem. So when you're solving a model using gurobi-py pandas, the aim should always be to get to a point where the model's solved and we extract the results of the model as pandas series, as a data frame, and take this kind of data in, data out approach and be able to cleanly work with the outputs in pandas. So what I've done here is applied a couple of accesses that we have in gurobi-py pandas for fetching some of the results. So Irv showed the retrieving the X attribute to get solution values. There's two more cases here we can use. So I previously captured the total active capacity in a pandas series. I can get the value of this active capacity from the current solution using this get value accessor. And I can also query the slack in constraints. So those capacity values had an associated constraint. All constraints in gurobi have an attribute called slack, which is measuring by how much the constraint, an inequality constraint might be over-satisfied. Right, so in this case, it's going to measure the excess capacity I have online beyond my minimum requirements. And these few steps have just created a Pandas data frame. So my variables are dealt with, they're gone. I'm back in Pandas data world, which means I can just throw together quite quickly a plot like this to show me over time how much total capacity I've got online versus the demand I was trying to satisfy and the excess capacity from those slack constraints. And that's all I have for that example. I'll throw it back to Irv to finish up.
Thanks, Simon. So we want to conclude here by again reflecting on why we believe this data-first model development is really a best way to go if you're developing applications for optimization. It's a proven practice. We have used it here at Princeton for many years for delivering high-quality optimization applications that are a lot more complicated than the ones you've seen today. And it starts with the 7 steps that you've seen here about understanding the data, defining and documenting your data sets, collecting data, documenting transformations. Then you write your model, and then you code the optimization model, and then you validate the results and potentially iterate as you see if the model is meeting your requirements. What we're very excited about is that by having Gurobi introducing gurobi-py pandas, this is taking advantage of pandas for managing data, which is really what I think it's second to none in terms of the ability for manipulating data, reading data, making transformations, etc. Allows the Gurobi objects to be placed in Pandas data frames in series, and it provides the capability to write code that really executes quickly when creating models. We've heard stories, and Gurobi, I've heard from my Gurobi friends of clients who wrote an application where it took 10 minutes to create the problem, and Gurobi solved it in a minute because the optimizer is so fast. And that's typically because they weren't writing efficient code to create the model. So using pandas with gurobi-py pandas really allows you to create efficient code for creating models. It does require some good knowledge of pandas and understanding how to map these mathematical formulations into gurobi-py pandas. And I've illustrated some of the techniques today of how to map math over to a gurobi-py pandas model. So I want to thank everybody for joining today. We've got some links in here. I'm pretty sure the slides will be shared and links will be shared. There's a documentation on gurobi-py pandas that's out there. It's a GitHub project. So if you have interesting ideas for improving it, I'm sure Simon would love to hear those ideas and contributions. We also have a blog here written by my colleague Rob Randall here at Princeton that goes into details, as I've discussed today, of our model development approach that's data first. And so with that, I'm going to turn the floor back over to Jennifer and Allison, who are going to moderate the questions.
Great, thanks. We had a lot of good questions come in, as well as some thank yous for the presentation. So to maybe start us off, you might want to hop back to your previous slide. But we did have a couple of questions around performance. So maybe this is a question for Simon as well. Have you compared the performance of Gurobi Pandas against kind of the more traditional interface or alternatives? And can you note the performance in terms of both model building as well as how it might affect the solution time?
Sure. So I haven't put together kind of comprehensive benchmarks. That's all kind of very dependent on the type of model that you're putting together. I think the main thing for me is what Irv just mentioned on the previous slide. So we've seen a lot of examples of model building code trying to use data coming from Pandas with the traditional gurobi-py API. And there's various ways that can kind of go wrong in the process of transforming the data across to using standard Python operations And we often see kind of too much kind of data manipulation logic integrated within the model building code that tends to slow things down. So I think the thing to focus on is that what gurobi-py Pandas tries to get you to do is put the input data into the appropriate format, this data first modeling paradigm that I was describing. And if you've done that, the code becomes very clean. You tend to avoid really bad performance bugs in formulating the model. And that I think we've seen is the kind of primary benefit. But there's not a kind of a massive speed up that you'll get in terms of a well-written model in either paradigm. I think the main thing there is really convenience and avoiding kind of really, really bad performance from data transformations. Yeah, certainly happy to put together some benchmarks at some stage if people are interested in that though. And on the model solving side, there's not going to be a big change, right? You're formulating the same model, passing the same model to Gurobi. So the optimization time I wouldn't expect to change. Do you have anything to add on that front, Irv?
Yeah, I would say two things. So we were using internally Pandas to create models before gurobi-py Pandas existed. And I would say in the 2018, so 5-6 years ago, we had some models that we had written both ways that were larger scale. And at the time, now again, that's based on that implementation of gurobi-py and our implementation of using Pandas, we were seeing that it was getting faster for models. One of the real issues that comes into play has to do with slicing. And so Pandas more naturally slices than gurobi-py does because it has some very efficient ways of doing these group by operations in an efficient way that I think is better than what's under the hood in gurobi-py. So now, I don't know if I did the same comparison today, how that would compare. In fact, one of probably the biggest things of overhead at the time was the naming of the constraints was actually the thing that was taking the longest. But the actual creation of the model was flying by in both cases. So it's useful to have names when you name your constraints and variables. It makes debugging your models a lot easier. But actually, there's an overhead for creating names that actually might be the most expensive part of this sometimes.
Yeah, for sure. So, and I think and something you don't want to miss out on if you need to debug a formulation. And we actually put some time in the latest version of gurobi-py into really sort of speeding up that process and making sure we didn't have any odd bottlenecks in Python. And that's something we've been able to leverage in gurobi-py Pandas. So building those constraint names sort of automatically is currently quite fast.
Great. Okay, that actually knocked out another question of kind of the advantages and drawbacks of using the new package, as well as thanks for sharing kind of what Princeton used to use to generate models. Maybe kind of along the advantages route, are there any advantage to this method versus maybe using Pyomo with Gurobi?
I'll take that one. What I have seen is, first of all, if you use gurobi-py instead of Pyomo, you will get better performance. The Pyomo is the way we avoid it, and we've looked at it, and our feeling is that its design was very much based upon AMPL, and AMPL is a model first way of thinking. And so, for example, I talked about earlier how we infer the sets of nodes and commodities from the tables, but in Pyomo, which is like AMPL, you have to actually explicitly say what those sets are and read them in separately. So it's that, to me at least, one of the real advantages here is that you're thinking about your data, you're working with your data, making sure you have good understanding of it. As you're developing a model in a notebook, you can be looking at the data, you can be plotting it, you can guess various different descriptive statistics, you can see where missing values are. And so you really get an understanding of the data, and then the data just plugs into a model that you write. In the Pyomo approach, you're really not making that necessarily data analysis and hooking it in the same way. And it's also just not as fast, especially when it comes to these slicing and group by operations. The gurobi-py pandas is just going to be a lot faster than using Pyomo.
Great. Thanks. All right. For the next question, maybe when dealing with large scale issues, do you find it more effective to define variables within a single data frame? So maybe allocating a column for each variable, or should you opt for individual data frames dedicated to each variable?
So I think this very much depends. I mean, you saw the approach in Simon's example, where because all of his variables were sharing the same index, he placed them all in a data frame. In the example that I did, which was quite simple, there was only one set of decision variables, so I have a series. In the models that we often create, there's typically a mix of variables that have different index sets. So you might say, if you think of like the classical facility location problem, and you're deciding what facilities to open, you'll have a variable that's indexed just on the facilities that you might open, and then you might have other variables that are going to be indexed on things like supply and demand and connections in a network. So in that case, you really are going to place them in separate series or data frames. In the larger models that we've developed here at Princeton, we almost always keep each set of decision variables in its own Pandas series, and that allows us to keep it straight from a development perspective. If we know we have that practice, then we're sharing code and we're collaborating, we all know that, hey, that's our best practice. I can see that all the variables are in a set of different series that are named however I want to name them. So that's typically what we do from our best practices here at Princeton.
Yeah, I guess it comes down to a sort of style difference sometimes, and it is dictated by the structure of the model. I tend to, at least the way I think about Pandas, so a data frame is just a collection of series that live on the same index. So for me, I actually find I keep it more straight in my head if the variables that live on the same index are stored in the same data frame. But the way we put gurobi-py pandas together is that whichever structure you prefer to use, there's a method for creating constraints in a similar way. So in a few cases in our examples, we use the accessor methods for creating constraints where you've got both sides of the constraint living in the same data frame. There's also functions if you've kept things separate in series to create constraints that way. So yeah, it really comes down to I guess preference and what best suits the model, what makes the cleanest code in each particular case.
Irv, could you, this was a question that came from your example. And the question was, why did you use the .ag instead of directly calling .sum?
Well, I think Simon alluded to that a little bit. We use .ag and then put grb.quicksum in there. And the reason is that on the larger scale models, as Simon mentioned, there is a bit of a better performance by using quicksum instead of using .sum. It's also knowing the Pandas internals of how the .sum works. I know it's going to be faster. So we've adapted as a best practice to use .ag with grb.quicksum because we know that as the models scale and get bigger, that will give us slightly better performance.
Thank you.
Oh, that's interesting. So I think another one for you, Irv. One of the issues that a customer noted is nested loops over indices can be a problem with variables with, say, maybe 2 or 3 indices. They're wondering how this library can handle this situation, or how would you handle such a situation?
Well, I mean, typically what happens is if you have, so there's a couple of things to think about here. So let's take this example of the multi-commodity flow where I had indices of my decision variables on products, a from node and a to node. Typically in a larger scale application, not every product can flow on every single arc. Furthermore, not every node is connected to every other node. It's not a complete graph. So the data is sparse. And in fact, one of the things that modeling languages and Pyomo don't really emphasize is taking advantage of the sparsity of data. So in this case here, if I had a larger scale network, I would read in just the connections that were in that network. So imagine having, and we've actually done for a customer a problem similar to multi-commodity flow with a lot more stuff in it, but they had a network probably on the order of about a couple of thousand nodes, and probably the number of arcs was maybe about 10 or 15,000 total. It's not 4 million. Not every node goes to every other node. So we're shipping over a big transportation network. When we do that, the result is that our decision variables are now indexed over these, like a product and a from and a to node, which are the kind of the three indices. So now if we need to state a constraint on just the products, we group by the product and then create our sums. Or if we need to do it on a subset of the index, we group by the subsets. This thing extends out. I think we once did a model that had 7 indices in it, and we had to group by various combinations of the indices, because when you write a constraint, you typically are saying, imagine you had sets A, B, C, D, E, F, G, and you're going to now state a set of constraints for the sets A, F, and G. Well, you group by A, F, and G, and then compute your sums and do whatever you need, and things line up. So the nice thing is that because if you take advantage of the Pandas multi-index, it's forcing you and really encouraging you to think about data sparsity, because typically the indices are going to be sparse with respect to the problem. Another example I've given in talks before is if you think about the classical assignment problem where you're assigning people to jobs and you had 1,000 people and 1,000 jobs. In the real world, not every person can do every single job. If they did, you'd have 1 million variables. Maybe each person is eligible to do only 5 or 10 jobs. That would be only 5 or 10,000 variables. You need to take advantage of the data sparsity when you create the model so that you take advantage of these multi-index types of things where you have lots of indices, as you were asking.
Thanks, Irv. We had a question, and this is a little more on the modeling side, that one of the attendees asked how you would create the surplus node using Pandas if the overall supply is larger than the demand?
Well, in that case, it's just a matter of it. I would have to extend the model. If I wanted to allow supply of a particular product to be larger than demand, all right, that means in that case, all I would do is I would change the constraint that was an equality constraint for net flow and just say that the supply, if I knew that the value was positive, I would say, okay, it has to be greater than, the flow has to be greater than or equal to, or I could add something into the network that would represent where to ship the surplus. So it really would very much depend upon the needs of the business. We think of having surplus nodes in the academic world. In the real world, if you got products to ship, you want to ship them everywhere, or they're going to stay where they were. And so you model that accordingly.
Thank you.
Thanks. Okay, so for our last question, we'll go to one that is kind of out of the box thinker. So maybe this is for Irv, but Simon, if you have any input as well, I'd be curious to hear that as well. So are you considering integrating any large language models into the data first approach way of modeling problems? They offered an example using LLMs to understand the data structure and extracting data values instead of kind of directly doing the coding for Pandas.
So the issue for us as a consulting firm is that when we get data, it typically belongs to our clients, and we have confidentiality and non-disclosure agreements. So there is no way that I'm going to take anything that looks like client data and give it to a chat GPT or an LLM. And it's not worth the expense of training our own LLM and taking one of the public domain and setting everything up and yourself in our own systems to do that, because our clients are paying for our time, but they're also paying for whatever computers that we need to do this. And as we all know, LLMs actually, if you start hosting them yourself, can be quite expensive to do so. So what prevents us from doing that is mostly this confidentiality issue of not sharing our client-specific information. And you have to be sometimes really, really careful. We have seen cases, we've had discussions with clients, as an example, where we've suggested using Gurobi Cloud, right? And all Gurobi Cloud sees is a matrix, right? You can't decipher any client-specific data from that. But the clients are saying, no, none of our data leaves our private cloud, period, end of story. They end up buying a Gurobi compute cluster, and they get the same types of things because security and privacy of data are paramount for most of our clients. So being able to use an LLM in that way, it's something we explore because of the confidentiality. Now, I believe if you're in a company and your company is comfortable with putting data out there and sharing your private information with OpenAI or anybody else, more power to you. I'm not so sure that there's that much of an advantage. One of the other things that happens too is our approach, which I had on the previous slide here, which I just lost, is really about documentation. This documentation is incredibly important, right? So we actually create a document that says, here's the list of tables. Here are the interrelationships between the tables, like when we're sharing keys between tables. Like, so for example, you saw in my example, I was sharing the nodes that are in supply and demand with the cost and the capacity. Those are all typically, if they came from a database, would be foreign key and have foreign key relationships. We document all of that information. We document assumptions about the data. Maybe an LLM would be able to do that type of thing. I probably would see it and say, I got to rewrite it because it's not going to be up to the standards that we here at Princeton Consultants have set that allow us to be efficient in terms of having different people take over work, etc. There may be a point in the future where some of these issues are overcome, especially the confidential aspects of data. It's a moving target and it's rapidly changing. So maybe my opinion might change in a year or two, but I frankly I tend to be a little bit more conservative when it comes to using any of these LLMs because of these confidentiality issues.
Yeah, it's a good point, and probably on the technical side, I mean, an LLM's not going to replace an Irv. I think we all know that, but but what we
or any of our other consultants for that
matter. But we have spent a little time looking into this, and the really exciting side of it, I think, is we've seen that LLMs can be really useful in kind of upskilling yourself to get the hang of some modeling techniques. So we've seen cases where it can actually do a reasonable job of sort of interpreting a requirement and showing how you might be able to model that in a mathematical program. It's not necessarily going to hand you a complete solution to the problem, but in terms of understanding how you translate a real world requirement into a mathematical model, it can really kind of help you get up the curve. And Alison, I think your team's had some good results as well in sort of getting quick answers to technical questions and pointing users in the right direction as well. So there's nice opportunities there. But I think Irv's right. It's not going to replace a full optimization system just yet, but it's definitely a useful tool to play with for helping understand some mathematical modeling techniques yourself.
Thank you again, and we hope to see you on our next webinar. Bye, everybody.